Chapter 13, Complex Reaction Mechanisms, Section 13.5, Adsorption and Desorption. In the adsorption and desorption mechanism, a critical parameter in evaluating surface adsorption is the fractional coverage, theta. Theta is defined to be the number of occupied sites over the total number of adsorption sites. So in this diagram, we can see 1, 2, 3, 4, 5, 6, 7. 7 sites, 7 surface sites are occupied. And now we have some unoccupied sites. I think if you count the unoccupied sites, we have 14 of them. So theta in this case is 7 over 21. The total number of sites is 21. 7 are occupied. So theta is 7 over 21, which is 1/3 in this case. The adsorption, desorption reactions can be expressed as these two equations. So R is the reactant in the gas phase. M denotes the surface sites. They react to form Rm, so occupied the surface sites. Alright, this is Rm. At the same time, this Rm, this absorbed species, may undergo desorption, alright, and to form R and a unoccupied site again. Alright, so these two equations can be used to describe the adsorption desorption mechanism. Okay, R is the species in the gas phase. M is the unoccupied surface sites. Rm is the occupied surface sites. So in this diagram, we have 7 Rm, 1, 2, 3, 4, 5, 6, 7. The 7 are considered Rm. And we have 14 Ms. Those are unoccupied sites, 14 blue ones. And we have this R, the blue ones in the gas phase. Again, R parenthesis G stands for the gas phase reactants. M stands for the unoccupied adsorption sites. Rm stands for the adsorption sites that is already occupied by R. Now, the adsorption rate is K sub A, the rate constant, times the pressure of R. So we have a P here, times the number of available surface sites or unoccupied surface sites, which is N times 1 minus theta. Alright, theta is the percentage of the occupied sites. So 1 minus theta is the percentage of the unoccupied sites. And this uppercase N denotes the total number of sites. Alright, again, this is the adsorption rate. Now let's look at the desorption rate. Well, it's K sub D times N theta. K sub D is the rate constant. N theta is the number of this Rm. In this case, the 7 red spheres absorbed on the surface already. Alright, so N theta is the number of occupied sites. And again, theta is the fractional coverage. D theta over dt can be expressed as, well, the rate of adsorption minus the rate of desorption. When adsorption and desorption reach equilibrium, d theta over dt is 0. Therefore, this minus this is 0. The adsorption rate is equal to the desorption rate at equilibrium. Again, when we have a equilibrium between adsorption and desorption, we have Ka, the rate constant for adsorption, times P, the pressure of the gas molecules, times N times 1 minus theta. N times 1 minus theta is the number of unoccupied sites. Now the desorption rate, K sub D, is the rate constant, and times theta is the number of occupied sites. the uppercase N and A cancel. N is the total number of sites. Now we have this equation. We can reorganize this equation. So KAP is equal to KD theta plus KAP theta. I'm moving theta to the right hand side of the equation. Now we can obtain the value or the expression of theta at equilibrium. Theta is simply KAP over this KAP plus KD. That's the expression of theta at equilibrium. This is the so-called Langmuir isotherm equation right over here. And then we can just have both the denominator and the numerator divided by K sub D. On top we have K over KdP. On the bottom we have K over KdP plus 1. And then we define the equilibrium constant for the adsorption desorption process. So this uppercase K is the equilibrium constant. It's the forward rate constant over the reverse rate constant. So in this case, it's K sub A over K sub D. Now the expression of theta is really simple. It's Kp over Kp plus 1. You can see this is almost always less than 1. Alright, so you can see this Kp on top, Kp plus 1 on the bottom, and therefore this has to be less than 1. Unless K is 0 or P is 0. Alright. Now we have this equation. What if we have experimental data of the value of theta at equilibrium and P at equilibrium? How do we analyze this equation? Well, apparently this equation is not linear equation. Theta is not linear with P. But if we take the reciprocals of both sides, then we have 1 over theta is equal to Kp plus 1 over Kp. And this is just 1 plus 1 over K times 1 over P. So now you can see 1 over theta is linear with 1 over P. We can plot 1 over theta versus 1 over P. The slope is going to be 1 over K. The intercept is just 1. So over here we have a simple graph of 1 over theta versus 1 over P. We have a slope of 1 over equilibrium constant, intercept of 1. This is also one of those double reciprocal plot. Let's look at one numerical example problem, 13.5.1. Let's look at this Langmuir isotherm equation. At equilibrium, theta is Kap over Kap plus Kd, and it can be written as Kp over Kp plus 1. This K is uppercase. The uppercase K is the equilibrium constant for the adsorption desorption process. And this uppercase K is equal to the lowercase K sub A over the lowercase K sub D. The adsorption rate constant divided by the desorption rate constant. And now we take the reciprocal of both sides. 1 over theta is Kp plus 1 over Kp. And 1 over theta is simply 1 plus 1 over K times 1 over P. By the way, why do we want to take the reciprocal of both sides? Well, it's just because we cannot separate Kp plus 1 in the denominator, but now we can separate this too, as the sum is in the numerator. We can separate this too. This is just a common technique for data analysis. So now let's have some experimental data. Let's say when pressure is 0.01 bar, theta is 0.2. When pressure is 0.02 bars, theta is 0.3333. Now let's make a plot over here and then determine the slope. The slope is going to be 1 over the equilibrium constant K. So we can actually make the graph. We can also do hand calculation. The slope is simply delta y over delta x. So on top we have delta y. Delta y is the difference between this 1 over theta values. On the bottom we have the change or the difference in 1 over p. So on top we have 1 over theta minus 1 over theta. On the bottom we have 1 over p minus 1 over p. Okay, this is the change of 1 over p. On top the change of 1 over theta. Do the calculation, we get 0.04, and therefore we determine the equilibrium constant. K is just 25. Or you can say the rate constant of adsorption over the rate constant of desorption is 25. In some cases, adsorption is accompanied by the dissociation of the adsorbate. For example, H2 may decompose on the surface and occupy two adsorption sites. So over here we have two equations. One is this R2, for example, a diatomic molecule reacting with two unoccupied sites to form 2Rm, and 2Rm can become this R2 in the gas phase, and then two unoccupied sites. Alright, in this case we can still write out the expression of d theta over dt. Again, what's the meaning of theta? Theta is the percentage of the occupied site. How does that change? Well, over here we have the adsorption rate minus desorption rate. The adsorption rate is the rate constant times P, which is the pressure of this R2, and then times, over here there's a coefficient 2 here, so we need to have the number of unoccupied sites squared. Alright, and then over here it's K sub D, the rate constant, times this is the occupied sites, and theta squared. Because of the coefficient 2, it has to be squared. At equilibrium, d theta over dt is 0, therefore this adsorption rate minus desorption rate is just 0. This equals this. We take the reciprocal of both sides, we get the square root. We take the square root of both sides, and then we get the square root of K times P, and then multiply by 1 minus theta equals the square root of KD, and then times theta. Now again, this uppercase K is the equilibrium constant for the adsorption desorption process. The uppercase K is the rate constant K sub A over the rate constant K sub D. Alright, and then we have this equation, the square root of Kp times 1 minus theta equals theta. We reorganize this equation. Theta is the square root of Kp over the square root of Kp plus 1. And again, we can see this is very likely smaller than 1 because Kp are typically just positive. K is always positive, and P is usually positive. Alright, P can be 0. That means if we have 0 concentration of R2 and then P is 0, right? But usually P is positive and theta is less than 1. And again, this K is the equilibrium constant. It's equal to the forward rate constant over the reverse rate constant. In this case, adsorption over desorption. And this time we need to actually make a plot of 1 over theta versus 1 over the square root of P, because we can take the reciprocals of both sides of this equation, and 1 over theta is the square root of Kp plus 1 over the square root of Kp. So 1 over theta is 1 plus 1 over the square root of K times 1 over the square root of P. So in this case, 1 over theta is linear to 1 over the square root of P. We make this kind of graph, 1 over theta versus 1 over the square root of P. The slope is 1 over the square root of K. The intercept is 1.